Planetary magnetic fields provide essential protection for surface environments, shielding atmospheres and potential life forms from harmful stellar radiation and particle emissions. These fields arise primarily from the dynamo effect of molten, electrically conductive material, typically iron, circulating within a planet's core, generating the electrical currents necessary to produce magnetism. Earth's robust magnetic field deflects the solar wind, a stream of charged particles continuously emitted by the sun, preventing these particles from directly stripping away atmospheric gases and bombarding the surface with radiation harmful to biological molecules. Planets lacking sufficient magnetic protection, like Mars, have lost substantial portions of their atmospheres over billions of years, resulting in thin, unprotected gas layers incapable of supporting surface liquid water or shielding potential life from cosmic radiation. The strength and stability of magnetic fields depend on multiple planetary characteristics, including mass, composition, internal differentiation, and rotational speed, with larger planets generally maintaining stronger fields due to their ability to retain internal heat longer. For planets orbiting red dwarf stars, magnetic protection becomes even more crucial, as these stars typically emit more frequent and intense flares and coronal mass ejections that could quickly strip away atmospheres of magnetically unprotected worlds. The presence of a substantial magnetic field thus represents not simply a beneficial feature, but rather a fundamental requirement for long-term planetary habitability, particularly for worlds orbiting more volatile stellar classes or located near the edges of traditional habitable zones. The geological characteristics of a planet significantly influence its ability to support life, with moderate geological activity providing numerous benefits while extreme conditions can render environments uninhabitable. Earth exemplifies a balanced geological system, with plate tectonics recycling carbon between the atmosphere and interior through volcanic outgassing and mineral weathering, helping regulate climate over billion-year timescales. This carbon cycle, driven by internal heat and crustal movement, constitutes a crucial planetary thermostat that has helped Earth maintain habitable conditions despite significant changes in solar luminosity throughout its history. Geological activity also creates diverse surface environments, mountains, valleys, ocean basins, that generate ecological niches conducive to biological diversification. However, excessive geological activity, such as runaway volcanism, can produce catastrophic outcomes by releasing overwhelming quantities of greenhouse gases or particulates that dramatically alter climates. Conversely, geologically dead worlds lacking internal heat sources cannot sustain the long-term cycling of elements necessary to maintain stable surface conditions. Evidence of past liquid water on Venus, the Moon, Mars, Vesta, and Ceres suggests that moderate geological activity may be more common than previously thought, potentially creating temporary habitable conditions on worlds not traditionally considered life-supporting. The complex relationship between internal heat, crustal dynamics, and atmospheric composition creates specific requirements for sustained habitability, explaining why searching for tectonically active terrestrial planets has become a priority in exoplanet research focused on identifying truly life-supporting environments beyond our solar system. The concept of galactic habitable zones recognizes that a star's location within a galaxy significantly influences its potential to host life-bearing planets through metallicity, the abundance of elements heavier than hydrogen and helium. Introduced by astronomers Peter Ward and Donald Brownlee in 2000, and further developed with Guillermo Gonzalez, this concept identifies regions close enough to galactic centers that stars are enriched with the heavy elements necessary for terrestrial planet formation. These metals, particularly iron, silicon, magnesium, nickel, and other rock-forming elements, originate primarily from previous generations of stars that synthesized heavier elements through nuclear fusion and dispersed them through supernovae explosions. Planets in metal-rich regions have access to the full periodic table of elements needed for complex biochemistry, including phosphorus for DNA and ATP, iron for oxygen transport in blood, and copper, zinc, and manganese for enzymatic functions. Metallicity typically decreases with distance from galactic centers, creating gradients of planetary system types. Metal-rich, inner regions tend to form more rocky terrestrial planets, while metal-poor outer regions produce predominantly gaseous worlds lacking solid surfaces. The requirement for sufficient metallicity constrains potential life-bearing systems to specific galactic regions, typically excluding the outermost spiral arms and many globular clusters where stars formed early in galactic history before significant metal enrichment had occurred. This metallicity dependence represents one of several factors defining broader zones of galactic habitability beyond the traditional focus on individual stellar systems. While proximity to galactic centers provides the metallicity necessary for terrestrial planet formation, these regions also present significant radiation hazards that can compromise planetary habitability despite favorable stellar conditions. The galactic habitable zone concept explicitly excludes regions too close to galactic centers, where intense radiation and frequent stellar encounters would disrupt planetary orbits and potentially sterilize planetary surfaces. Near the supermassive black holes residing at most galactic centers, extreme X-ray and gamma-ray emissions create hostile environments for complex organic chemistry, potentially damaging biological molecules and disrupting delicate cellular processes necessary for life. Similarly, areas of active star formation present radiation challenges through frequent supernova, massive star explosions that release enormous amounts of high-energy radiation capable of stripping away planetary atmospheres and triggering mass extinction events if occurring within approximately 30 light-years of inhabited worlds. The rates of these cataclysmic events vary significantly across different regions of galaxies, with bulges and dense spiral arms experiencing more frequent stellar explosions than sparser regions between spiral arms. This spatial variation in radiation hazards creates a complex pattern of habitability across galaxies, with optimal zones located at intermediate distances from galactic centers, far enough to avoid extreme radiation environments but close enough to benefit from metal enrichment. These competing factors help define broader galactic habitable zones that encompass regions where the balance between metallicity benefits and radiation hazards creates the most favorable conditions for life-supporting planetary systems. The density of stars within different galactic regions creates varying levels of gravitational stability, significantly influencing the long-term habitability of planetary systems through potential orbital disruptions. In densely packed regions like globular clusters or galactic centers, close stellar encounters occur relatively frequently in astronomical terms, potentially altering planetary orbits or even ejecting planets from their home systems entirely. These gravitational perturbations can transform circular, stable orbits into eccentric paths that cause planets to experience extreme temperature variations as they move closer to and further from their host stars, potentially rendering otherwise habitable worlds unsuitable for continuous liquid water and stable ecosystems. The galactic habitable zone concept accounts for these density effects, favoring regions with sufficient spacing between stars to minimize disruptive encounters over the billions of years typically required for complex life to evolve. Our Sun resides in a relatively low-density region between spiral arms, experiencing few close stellar approaches that might disturb the orderly architecture of our planetary system. This gravitational stability has allowed Earth to maintain a relatively consistent orbit and climate conducive to biological evolution over geological timescales. The requirements for long-term orbital stability further constrain potential life-supporting regions within galaxies, creating another parameter that must be optimized alongside metallicity and radiation protection to identify the most promising environments for complex life to emerge across our galaxy and potentially throughout the universe. The duration of habitable conditions represents a crucial but often overlooked factor in assessing where life might develop, requiring stable environments maintained over the immense timescales needed for biological evolution. Earth required approximately 4 billion years to progress from simple prokaryotic cells to complex multicellular organisms and intelligent life, suggesting that similar evolutionary trajectories elsewhere would demand comparable periods of environmental stability. The galactic habitable zone concept incorporates this temporal dimension, identifying regions where planets can maintain habitable conditions long enough for complex life to potentially emerge and thrive. Various factors influence this longevity. Stars near the end of spiral arms experience relatively rapid orbital changes around galactic centers, potentially exposing their planetary systems to varying radiation environments and stellar densities as they move through different galactic regions. Conversely, stars in more circular galactic orbits maintain more consistent galactic environments over billions of years. The age of galactic regions also matters significantly, as extremely young stellar populations haven't existed long enough for complex life to evolve, while the oldest regions may contain stars approaching the end of their main sequence lifetimes, with continuously increasing luminosity, potentially pushing planets out of habitable zones. These temporal considerations create a four-dimensional concept of habitability, three spatial dimensions defining regions within galaxies, plus the critical time dimension determining how long these regions remain conducive to life. This comprehensive approach helps identify not just where life might exist currently, but where it has had sufficient time and stability to potentially evolve into complex and possibly intelligent forms capable of developing technology and civilization. The discovery of thriving ecosystems deep within Earth's crust has dramatically expanded our understanding of potential habitable environments, suggesting that life might exist in subsurface regions of worlds previously considered hostile or uninhabitable. These deep biosphere environments operate independently of stellar energy, relying instead on chemical energy sources from mineral reactions, radioactive decay, or residual heat from planetary formation. Earth's subsurface harbors vast microbial communities extending kilometers below the surface, surviving in porous rock spaces, fracture networks, and even isolated water pockets where they metabolize hydrogen, methane, iron, sulfur compounds, and other reduced chemicals. This revelation has profound implications for astrobiology, as bodies beyond traditional habitable zones might support similar subsurface ecosystems regardless of harsh surface conditions. Mars, with evidence of past surface water and current subsurface ice deposits, could potentially harbor microbial life deep underground, where radiation protection and stable temperatures provide more favorable conditions than its oxidized, radiation-exposed surface. Even more compelling are ocean worlds like Europa and Enceladus, where substantial liquid water oceans exist beneath thick ice shells, heated by tidal interactions with their massive parent planets, rather than direct stellar radiation. These subsurface oceans remain liquid despite their great distance from the Sun, existing far beyond traditional habitable zone boundaries, yet potentially providing all the necessary ingredients for life: liquid water, essential elements, energy sources, and protection from radiation. The recognition of these alternative habitable environments has fundamentally expanded our search parameters, suggesting that even rogue planets ejected from their star systems might harbor subsurface conditions where simple life could potentially survive indefinitely without stellar energy. Tidal heating represents a powerful alternative energy source that can maintain habitable conditions on worlds located far beyond traditional circumstellar habitable zones, potentially creating environments conducive to life in unexpected locations. This heating mechanism results from gravitational interactions between a planet or moon and a massive parent body, with the varying gravitational forces causing the smaller body to flex and stretch, generating significant internal heat through friction. Jupiter's moon Io dramatically demonstrates this process, with tidal interactions producing intense volcanism, despite receiving minimal solar warming at 5.2 AU from the Sun. More intriguingly, moons like Europa, Ganymede, and Enceladus appear to maintain vast subsurface oceans through tidal heating, creating potentially habitable environments in regions once considered too cold for liquid water. This alternative energy source has prompted the development of the circumplanetary habitable zone, or habitable edge concept, encompassing regions around planets where moons can maintain stable orbits close enough for significant tidal heating without experiencing disruptive forces that would destroy them. Such tidally heated environments offer distinct advantages for potential life. They remain stable over astronomical timescales regardless of the parent star's evolution, provide consistent energy, independent of day-night cycles or seasonal changes, and typically exist beneath protective ice shells that shield them from radiation and meteorite impacts. These characteristics have led astrobiologists to prioritize tidally heated ocean worlds like Europa and Enceladus in the search for extraterrestrial life, recognizing that such environments might actually offer more stable long-term conditions than planets directly dependent on stellar heating, particularly around variable or aging stars. Alternative atmospheric compositions and extreme pressure conditions could potentially create habitable niches in environments previously considered incompatible with life, significantly expanding the range of worlds worth investigating for biological potential. Planetary mass objects with atmospheres containing high concentrations of greenhouse gases might maintain surface or subsurface liquid water at greater distances from their stars than traditional habitable zone models suggest. Super-Earth planets that have retained extremely dense atmospheres with surface pressures up to 100 kilobars could experience sufficient radiative forcing to maintain liquid water, despite receiving minimal stellar radiation. Water itself demonstrates remarkable adaptability under varying pressure conditions, remaining liquid at temperatures far above its normal boiling point in high-pressure environments, or existing as brines with significantly depressed freezing points when mixed with salts or ammonia compounds. These pressure and compositional effects create potential habitable niches in surprising locations. Deep within Venus's atmosphere, where temperatures and pressures approach Earth-like conditions, or beneath the high-pressure hydrogen-rich atmospheres of mini-Neptune-type worlds common throughout our galaxy. Additionally, atmospheres dominated by gases other than nitrogen and oxygen might support entirely different biochemistries. Methane-based life in the hydrocarbon lakes of Titan, for instance, or silicon-based organisms in highly reducing hydrogen-rich environments. While speculative, these possibilities acknowledge that life might exploit different atmospheric chemistries and pressure regimes than those familiar from Earth, requiring astrobiologists to consider a broader spectrum of potentially habitable conditions beyond those that would be comfortable for humans or Earth-evolved organisms. Research into Earth's extremophile organisms, life forms thriving in environments once thought uninhabitable, continues to expand our understanding of the physical and chemical boundaries that might constrain life throughout the universe. These remarkable organisms demonstrate surprising adaptability to conditions previously considered prohibitive. Thermophiles flourishing in hydrothermal vents at temperatures exceeding 120 J. Psychrophiles metabolizing in ice at 20 J. Halophiles thriving in salt concentrations that would dehydrate conventional cells. Radio-resistant bacteria surviving radiation doses thousands of times greater than human lethal levels. And barophiles adapted to crushing deep ocean pressures exceeding 1,000 atmospheres. Each extremophile discovery extends the known environmental parameters compatible with life, suggesting that habitable conditions might exist across a much wider spectrum than traditionally assumed. This expanded understanding has directly influenced astronomical habitability assessments. The recognition that life can utilize chemical energy sources independent of photosynthesis supports the potential habitability of subsurface environments like Europa's ocean, while the discovery of organisms metabolizing hydrogen, iron, and sulfur compounds enhances interest in the habitable potential of Mars, with its iron-rich regolith and potential subsurface hydrogen sources. The remarkable resilience demonstrated by Earth's extremophiles suggests that life, once established, might adapt to gradually changing conditions that would otherwise appear prohibitive if encountered abruptly. This adaptability further complicates habitability assessments, as worlds currently experiencing extreme conditions might have harbored more moderate environments in their past, potentially allowing life to emerge and subsequently adapt to increasingly challenging circumstances. These insights from extremophile research continue to shape and expand our conceptualization of habitable environments, suggesting that life might exist in a surprisingly diverse array of astronomical settings beyond traditional habitable zone boundaries. The search for environments capable of supporting life throughout the universe represents one of astronomy's most profound and complex endeavors, requiring the integration of multiple scientific disciplines and continuously evolving models. The traditional circumstellar habitable zone concept, while providing a useful starting framework, has expanded significantly beyond its original water-centric, stellar energy-dependent formulation to encompass a diverse array of potential life-supporting environments. This evolution reflects growing recognition that habitability depends not merely on orbital distance, but on complex interactions between planetary mass, atmospheric composition, geological activity, magnetic field strength, and numerous other factors that must align to create truly life-supporting conditions. Conservative estimates place Earth at the inner edge of our Sun's habitable zone, highlighting how precisely balanced our planet's conditions appear to be. Yet more optimistic assessments suggest habitable conditions might exist from Mercury's aphelion to beyond Saturn's orbit under specific circumstances. Beyond individual stellar systems, the galactic habitable zone concept identifies regions within galaxies offering optimal combinations of heavy element availability, radiation protection, and orbital stability necessary for life-supporting planets to form and maintain favorable conditions over evolutionary timescales. Perhaps most significantly, the recognition of alternative energy sources and environmental niches, subsurface oceans maintained by radioactive decay or tidal heating, exotic atmospheric compositions creating greenhouse conditions in distant worlds, and potential biochemistries utilizing different solvents than water, has fundamentally expanded where we might find life-supporting environments throughout the cosmos. As we continue exploring these diverse possibilities, the question of where life might thrive increasingly appears limited, not by the rarity of suitable conditions, but by our expanding understanding of life's remarkable adaptability and the universe's astonishing variety.